Okay, welcome back, everybody. My apologies for the lateness. I was having a little bit of a technical problem. Okay, any questions? Just a heads up, you have the next exam a week from today. So we'll be done with this chapter today and definitely jump into the next one and chapter 9, and then we'll be done with chapter 9 on Thursday. All right. Let's start off with where we were. We've been talking about the chapter on nomenclature, basically naming compounds. Not only that, learning how to put them together, okay? The key aspect about putting them together, specifically for the ionic compounds, is to first put them into ionic form, then put those together, put the ions together with enough cations and anions so that they balance each other out and cancel each other out. So sometimes it's a straightforward one cation, one anion. Sometimes it's 2 to 1 or 2 to 3, any combination. So, and this page we ended up in wanting to figure out, okay, give the name and the formula. So let's first write the formula. The number 1 is strontium. We have to first find it, Sr. Sr is a group 2 metal, and it has a +2 oxidation state when it becomes ionic, okay? And then we have the hydroxide, which is given here. And so, and the OH is a -1, so that means we need 2. So with respect to putting them together to write a formula, we have SR parentheses O2. Remember, when we need more than one of the polyatomic ions, more than one, we put a parentheses around it and then use a subscript to designate how many of those we need, okay? We'll come back to the name here in a bit. The next one, it is Au, which is gold, okay? And then we got the Cl, which is chloride. So I write the base name, but the question is this: I don't know what the oxidation number is for gold. Why? Because remember, it's not part of the 16, therefore it has a variable oxidation state. It can vary, and those variable oxidation state metals can go from a +1 to a +9. It can vary. So in here, what we got to do is we got to calculate. So we know that the chlorides are each -1, and therefore that means that we have a total of -3 for all the chlorides. That tells you that the gold must be a +3 to cancel out the total -3 of the chlorides. Therefore, the name is gold, parentheses, Roman numeral 3 in uppercase, in parentheses, chloride, okay? All right, then we got zinc and oxygen. Well, zinc is one of the 16, so it has a +2 charge. The oxygen becomes oxide, so it has a -2. We put them together. We can simply put them together as a 1-to-1 ratio, so it becomes ZnO. Okay, for the formula. And we'll get to the name here after we're done with the formulas. All right, the next one is number 4. We have barium, which go to the periodic table. Barium is a group 2 element, specifically metal. We'll lose electrons. It will have a +2 charge, oxidation number. The phosphate has a -3. It is a polyatomic ion. So now we have a dissimilar here between a +2 and a -3, which we need to put together. Well, to put those together, I'm going to need 3, find a common number. In this case, as we've been doing with the other ones, in this scenario, it's common number 6. So we need 3 bariums to give us a total of +6 for the bariums, and we need 2 phosphates to give us a total a of -6. So those coefficients become the subscript. So we have barium, subscript 3, since we need 2 phosphates, parentheses, so that becomes PO4 and parentheses 2, okay? Another way to look at that too is this. Notice that the oxidation number, the charge for the anion, becomes the subscript for the cation. And the charge for the cation becomes the subscript for the anion. So that's another aid to help you to make sure you put them together in the right ratio. Otherwise, if you don't see that, do it like the way we just did, okay? Excuse me. So here we have SO3, which you might think sulfate, polyatomic ion. However, it's SO3. And when you look at the polyatomic ion table, that is called sulfite, okay? It's a sulfite. The lithium is a group 1 metal. It has a +1 oxidation number when it becomes an ion. That means we need two lithiums for every sulfite, okay? So that becomes, formula is Li subscript 2 SO3. Remember, when you only need one of the polyatomic ions, whichever one you need, no parentheses is necessary. All right. Aluminum is a group 3 metal. Will have a +3 oxidation number when it becomes an ion. Sulfur is in group 6. It will become a -2. It's a nonmetal. Will gain 2 electrons. It needs 2 electrons because it's in group 6. It needs 2 more to fill up that valence shell to give it an 8. Get that magical 8 number. All right. So here again we have dissimilar charges like we had in number 4. And so in this case we are going to find a common number again. So we need 2 aluminums. A common number in this case is 6. We need 2 aluminums. It gives us a total of +6. Okay. 1 second. Okay. +6 for aluminum. And we need 3 sulfides to give us a total of -6. Therefore, our formula becomes Al subscript 2 S subscript 3, okay? Aluminum sulfide would be the name here. All right, and then finally, let's do this last one. Again, as the case with number 2, we're working with copper here, which has a variable oxidation number, and we don't know which one it is, so we need to calculate it. We see that we have in parentheses a polyatomic ion, specifically the NO3, which is specifically the nitrate. And that means that if you look that up, it also has a -1 charge, okay? There's 2 of the nitrates. So we have a total of -2 for both the nitrates. So in order for that total charge to be equal to 0, that implies this copper must be a +2, okay? Which means that now that the parent name is copper, we didn't know what the parenthesis is, and then nitrate, that is the name for the polyatomic ion. It is not nitrogen trioxide, it's not that at all. It is nitrate because it is a polyatomic ion, okay? Nitrogen trioxide would be a covalent compound, right? And then we just calculated what the oxidation number is for copper. It is a +2, so we use Roman numeral 2. So that is copper 2 nitrate. But let me get the other drawing here, and that way you can see it better than my hand drawing. The first one was the formula we did. The name was strontium hydroxide. Number 2 was gold 3 chloride. Number 3 is the formula ZNO, has the name zinc oxide. Notice we use no Roman numerals for the metal because it's part of the 16, has a constant oxidation number. We know it is always a +2, therefore we don't need to use Roman numerals for zinc. or for that matter, strontium. Strontium is in group 2, and the same is true with barium, number 4. The formula we just did, its name is barium phosphate. Okay, and then we got lithium, also true for lithium and aluminum. Okay, for the next 2 is the name is lithium sulfite. Okay, if you wrote sulfate, that would be incorrect because the formula is SO3. Okay, the sulfate, and then copper nitrate. Let's go to that polyatomic ion. If we zip through that, you can see right here, we were working with the sulfite. Okay. All right. And then, oh yeah, we got the copper 2 nitrate. So here, let's do another set, and again, mix and match. Okay, because even we start with strontium, but we can combine that with the chloride and the oxide and the phosphate and the sulfite and the sulfide and the nitrate. Okay, so and we do the same with the gold hydroxide, gold zinc, gold oxide, gold phosphate, gold sulfite, etc., etc. So again, your database of compounds that you can put together is slowly increasing more and more. Okay. All right, the next one here, they're asking you to give the formula. Okay. All right, so when we're given the name and we want the formula, we need to first write everything in ionic form. So we got sodium. Sodium is a group of 1 metal. It would have a +1 charge, oxidation number. Okay. We have nitrite, not nitrate, but nitrite. And if you look at the polyatomic ion table, you'll see that that is NO2 -1. Okay, so we can ideally just put them together as a 1-to-1 because we got a +1 and -1. The formula would simply be NaNO subscript 2 nitrite. Okay, nickel 3 oxide. All right, so the Roman numerals telling us that we are working with nickel, which is Ni, and we're working specifically with the +3 ion. The oxide is a -2. So now we have a dissimilar charges here. Okay, so we find a common number. So we need the common number again in this scenario is a 6. Now, most of the time, the common number is a 6, but it can be, any other number. It could be something else. So, but so far, it's common number 6. So we need 2 nickels and 3 oxides. Okay, so the formula becomes Ni2O3 for nickel Roman numeral 3 oxide. Magnesium iodide, and magnesium is a group 2A metal, has a +2 oxidation state. Iodide, not iodine, but iodide tells you that is the I -1, okay, the ion. We need 2 of the iodides for each magnesium, so the formula is Mgi subscript 2. All right, the cyanide, that is a polyatomic ion. It has a -1 charge, Cn -1. Aluminum always has a +3. That means we need 3 cyanides for every aluminum ion. So the formula becomes aluminum parentheses Cn subscript 3. Okay. All right. Clear this up. And there you go. Okay. Also, again, remember that you can take the sodium and combine it with the oxide, sodium with the iodide, sodium with the cyanide, okay? And if you did that, that would be sodium nitrite, excuse me, and then sodium oxide, sodium iodide, and sodium cyanide, okay? And do the same with nickel and nitrite, nickel with iodine, nickel with cyanide, etc. So again, probably up to about 400 or 500 compounds now, maybe. All right, so with respect to, now that's with ionic compounds. Ionic compounds, let's rehash for a second before we move on to covalent. To write the formula for ionic compounds, you need to take the element, convert it to the ion. Okay. Then once you have the oxidation number of both the cation and anion, put them together such that you have enough of each to equal 0. Okay. With respect to naming them, no prefixes. Okay, no prefixes. So in the magnesium, the one we just did here. This, like I stated, its name is magnesium iodide, not magnesium diiodide. So no prefixes. Okay. And second point is this: for the 16, the good old 16 metals, no Roman numerals. Okay, no Roman numerals. That means that all the other metals, like nickel here, requires a Roman numeral, so you know it will either be given to you, so you can write the formula, or you need to calculate which one it is. Okay, and then use the Roman numerals to in the naming process. Like this one is nickel 3 oxide. Okay, all the other 16, since we know their exact oxidation number, no Roman numerals are required. All right, so which brings us to covalent compounds. Now, the anion part of the like the sulfur, the oxygen, the phosphide, their naming changes also in molecular compounds. It stays. So oxygen is oxide, be it as an ionic compound or as a covalent compound. Okay. For example, if we were to write sodium oxide, okay, sodium oxide, the name for oxygen is oxide. Now, if this was in covalent compound, carbon monoxide, notice the oxide remains the same, okay? Carbon monoxide. Now, in ionic compound, the sodium 99% of the time is written first, followed by the anion part, okay? In covalent compounds, there always will be the central atom. The central atom is written first. So in this case, carbon is written first. And then what follows is whatever is bonded to the central atom. Okay, so, and that's how you can right away know I'm dealing with ionic compound here, simply because I'm dealing with sodium off the top, right up front. Right, when you don't see any metal in the formula written, then you're dealing with a covalent compound. And so, furthermore, you know that the first element written is the central atom. And that being the case, that central atom's name remains whatever its name is. Okay. So carbon remains the name carbon. We don't change the name for that. All right, so we know that we are dealing with nonmetals only, and obviously we don't have ions. We have no hardcore charges like the ionic compounds, but we do have partial charges, okay? So we do have oxidation numbers. That's why we use oxidation number in lieu of saying charges. And occasionally I slip, but I try to maintain. I call it oxidation number if it's a ionic or a covalent. Okay. We do use the prefixes to describe the number of atoms that are bonded to the central atom. Okay. Now, if there's only one atom bonded to the central atom, like I just did carbon monoxide, then we use the prefix mono, which is one. So mono is one, di is two, tri is three, tetra is four, penta is five, hexa is nine, hepta is seven, octa is eight. Normally we don't go any higher, but if we did, the nine, this is nine, NONA, and then deca is 10, okay? And so the prefixes, like I stated earlier, we have CO, which is carbon monoxide, versus CO2, which is carbon dioxide, okay? So that second metal, excuse me, that second non-metal, if there's one, we put mono, or we put a prefix to describe how many of that second element is bonded to the central atom. And we use mono, di, tetra, whatever we need, okay? All right. Okay, so basically we had the system written is you have the first non-metal written here in green, okay? It may or may not have a prefix. If it is just one atom, then we would simply say the name, no prefix mono. Notice I said CO, carbon monoxide, CO2, carbon dioxide. So there's only one atom up front, so we don't need a prefix. If there's more than one, then we need a prefix. If this was, crazy, it's not a formula, but this is a FYI, this is not a formula, but if it was a formula, C2O2, we would say dicarbon dioxide, okay? But I emphasize this is not a formula. I'm trying to demonstrate what the green part says, okay? So this is not a true formula. Then the second one, we use a prefix, always be a prefix, even if there's one, where we use the mono and then followed by the non-metal name with the ide. So an oxygen becomes oxide, okay, monoxide, dioxide, trioxide, tetraoxide, et cetera, et cetera. All right, so as I stated here, we don't use mono if the first element is all by itself. So as stated, carbon dioxide, okay, no prefix. The atom is all by itself. The first central atom is all by itself. All right. So this one here would be carbon monoxide. Okay. All right. Now let's break this down. The first metal would be considered the central atom. There's two of them. Yes, you can have more than one central atom. So what we do here is we write the base name and then come back and do the prefixes. So the base name would be phosphorus. Okay. We don't say phosphide. When it's the first element, it is phosphide. If the phosphide was second, is the phosphorus was second after the central atom, then yes, it would become phosphide. Okay, we'll have some examples of that in a minute. And then we got oxygen, which will be oxide. Okay, so that is the base name, phosphorus oxide. Now we go back and add the prefixes. There are two for phosphorus, so it becomes diphosphorus. And then there are five. So 5 is penta. Now here's the thing for correct English notation. You have penta, which ends in an A, which is a vowel, and then you're going to connect it to another word that starts with a vowel. So technically you're supposed to drop the A and write pentoxide. Okay. but I'm not going to be that big of a stickler for that. So if you happen to write pentoxide, leave the A in there, that's fine. I will not take points off for that. Okay. All right, so diphosphorus pentoxide. Now keep in mind, you need to be able to go backwards too. Lost my connection. I'm getting my technical problems back. I'm assuming everybody can hear me okay? Yeah, okay. Well, thank you. I don't know, it just went blank. Let's go back. There we go. All right, so we may end up with 2 recordings here. I don't know. See how Zoom handles that. It's happened in the past where it drops the Zoom closes, and I end up with 2 recordings. So if I do, I'll call it part 1, part 2. Okay. All right. So we got diphosphorus pentoxide, as I was stating. Be able to go backwards, so you can be given the name, and you're wanting to determine the formula. Okay. Those who just came back, we lost contact, but we're back online. And letting a few come back in. Okay. So work it backwards. So like I just did with this, I first wrote the base name, phosphorus and oxide. Then I came back and added the prefix. Remember, there's no, if that phosphorus was only 1, then it would be just simply phosphorus. There's 2, so it becomes di. And then the prefix for 5 is penta. Technically, we should drop the A. All right, and either way will work fine. I'm not going to take off if you forget to leave the A. So then be able to work backwards, you might be given the name and asked to get the formula. What would you do to work backwards? You get the base name again, the base formula. We got phosphorus and we got oxide. Okay, I write that down. Then I come back and I figure out the prefix, and it's 5 for the penta and 2. And so I work it backwards. Okay. So be able to go both directions if necessary, depending on the question. All right, so here we have phosphorus, okay? And so we can write phosphorus, the base name, and then we have F, which is fluoride. Okay, that's our base name. And then we come back and do the prefixes. There's only 1, so we don't need to put a mono in front, just 1, but there's 3 fluorides, so it's trifluoro. So that is phosphorus trifluoride. Okay. Now, notice here, there are examples where some of the halogens can be the central atom. Normally, we think of iodine as just, being a negative charge and it's attached to the central atom. Some of the larger elements can be the central atom. So in this scenario, iodine is a central atom, okay? And so therefore, being the first element, its name is whatever its name is an element, iodine, okay? Then we got the fluorides. You won't ever find fluoride as a central atom. Fluoride is always bonded to something, even to itself. And so this is fluoride. Okay, so that is the base name. We go back and look if there's any prefixes. No for iodine, but we have 7 for fluoride. So heptafluoride. Here we can technically leave the A there because F is not a vowel. So it's heptafluoride. Okay, Now, given the formula, write the name. So here we go. Now here's another example where normally we think of the Br is either bonded to itself or as a bromide. But it's feasible that the bromine can be bonded to oxygen. There's a whole series of bromates and bromides out there. So we have bromine, parent name. Okay, so it's bromine, not bromide. I can't overemphasize that it is not a bromide, okay? Because bromide infers that would follow. In other words, there'd be some other atom, and bromide would be bonded to the central atom. That is what you infer when you see the IDE. The fact that it is written first tells you it's bromine, okay? And then we got oxide. Okay, so now the prefixes, we got 3 of them, so that's tribromine, and then we got octoxide. So some of these are, with the prefixes, can be a little bit of a tongue twister. There we go. So technically, as I stated, that A should be away, so it would be octoxide. So tribromine octoxide. All right. Now we have phosphorus is the central atom. And these are very complicated looking compounds. They're really actually complexes because here you got 4 phosphorus, and then you got 7 sulfurs bonded to the central group of 4. So it's phosphorus. And then since sulfur follows, it would be sulfite. Okay, here's a good example to distinguish between sulfur versus sulfide. In the next example, well, I think it's there, but let's just go with this example. Okay, sulfur is bonded first, so in this case, it's simply sulfur. Okay, here, sulfide follows the central atom, so it is sulfide. Okay, notice the distinction. Okay, now obviously this would be oxide. And then dioxide. Right. So we have here tetraphosphorus heptasulfite. Okay, heptasulfite. Here's I guess it's there, but it's 3 oxygens. We have sulfur, and then 3 oxides, which would be sulfur trioxide. Again, here sulfur is the first element, so it remains sulfur, not sulfide, like the previous example. And then here you have the name, and you need to determine the formula. So as we were doing with the names, here you write the base formula, which is iodine and fluoride. Okay, the fluoride and the iodine. Now you go back and look at the prefixes, and we got 6 fluorides. So that formula would be IF6. Okay. And then now you're being asked to, again, give the formula. So we work it backwards. You got chlorine and then oxide. So Cl and then the oxide, and then go back and do the prefixes, 2 chlorines, di, and 5 oxides. So its formula will be Cl2O5. Okay. And then here we want the name. So we have, as the second example we did earlier, we have phosphorus up front, and then iodide. Okay, go back and do the prefixes. So that would be 2, and then tetra iodide. Okay, diphosphorus, tetraiodide. All right, so a few reminders, prefixes only for covalent compounds, okay? Roman numerals only for those metals that have a variable oxidation number. And so there's 16. And a question. All right, let me go back. Sure, I'll go back. Right here. Sorry, I went too fast. Okay. You got it okay? Okay. Now, all right, yeah, no worries, you're welcome. Now, here, like I said, you're given the formula, give the name, or given the name, write the formula. So be able to go whichever direction. That's true not only for the covalent compounds, but for the ionic compounds, okay? All right, so as I was stating, reminders, prefixes only for the covalent compounds. If the covalent compound only has one central atom, the first element, I should say, no mono, just whatever it is, okay? Only if you have more than one, then you put the prefixes for the name. Roman numerals are only for those metals that have variable charges, variable oxidation numbers. Remember, there's only 16 that do not. Refresh your memory. Go back to the periodic table, and it's those guys I circled in red. Group 1, group 2, there's 12 of them right there. And then I got aluminum, zinc, silver, and cadmium, 4 more, which gives you the 16. That means every other metal involved there, every other metal has a variable oxidation number, okay? And therefore require the use of Roman numerals to distinguish them apart. The polyatomic ions, we don't change their name. They each have a given name, and that's what it is, okay? Like nitrate, that is not nitrogen trioxide. Okay, that's important. That is not nitrogen trioxide, or if it was the nitrite, which would be the NO2, okay, the NO2, that would not be nitrogen dioxide, because the NO2 with a negative charge tells you it's a polyatomic ion and therefore has its own specific name. The other thing to remember about the polyatomic ions is if you need more than one, use a parentheses, okay? Use a parentheses with a subscript to show how many of those polyatomic ions you need. All right, so here, give you a minute or so if you want to run through those. It's asking you here to write the name, okay? Sort of like a speed test, right? No, you got BaCl2. Okay, I'll go through it. First thing to realize that one, barium and Cl2, I have an ionic compound. Being ionic, no prefixes, okay? Second of all, it's ionic, though I have to think about Roman numerals. Well, barium is part of the 16, therefore, no Roman numerals. Okay, so I can go strictly barium for that ion. I first need to write these in ionic form. So barium is a +2, okay, just to make sure that the form is correct. I'm writing the name here, and the chlorides are each -1. At 2 of them, yeah, that form is correct. I always check the formula, just to double check that I don't have a typo here. Because if you were to see something like this, okay, you should look at that and you might think, wait a minute, okay, is that even feasible, BLCl? And the answer is no, okay? Why is that? Because the bariums have a +2. The chlorides always have a -1. I need 2 chlorides, so there should be a subscript 2. And so this will be incorrect and as a choice for a formula. Okay. Okay. FYI. All right. So with that being the case, everything looks good. Its particular name would be barium. All right. Obviously, going to take more than 3 minutes because I'm going through each step to explain why. All right. NO2, no charge. Okay. So it's not a polyatomic ion. Notice if it would have been written as follows, and then that is called the nitrite. Okay, polyatomic ion. So here we don't have that, so it's covalent. And so we have base name nitrogen, and then oxide. Okay, then we go do the prefixes. We only have 1 nitrogen, so that remains nitrogen, and then we have two oxides, so it's dioxide, nitrogen dioxide, not nitrite. Okay. Next one. Yeah, you have 2 options here. Can you remember what I stated, what I showed you when you have, I'm having this fairly complicated formula here. Looks complicated, but let's break it down. Okay, it really isn't as complicated as it looks. Okay, let's break it down. First of all, I see parentheses. Okay, that tells me polyatomic ions. All right, so that sends me to the polyatomic ion table. Look for a PO4. Sure enough, there's a PO4 -3. Okay. Iron is not part of the 16. So that means that I need to have a Roman numeral of some sort here. So the base name, they give me the formula, they want me to give you the name, so I can very quickly write iron, parentheses, and then phosphate. Okay, but I don't know what goes in here. I need to figure that out. So the parentheses sent me to the polyatomic ion table. I determine it's phosphate. Okay, there's 2 of them there. All right, and there are 3 irons, so I can write a general formula. First of all, I got a total of -6 for the phosphates. Okay, so I have 3 irons -6 equals 0. Okay, so I can quickly now generate this simple algebraic equation, 3 irons, because I got 3 irons, -6, because each phosphate's a -6, and there's 2 of them, equals 0. So I need to solve for iron. So when I do that, I got iron, 3 iron is equal to +6. Divide through by 3, iron is equal to +2. Okay, so that means I'm going to use Roman numeral 2 here. Okay, so it's iron, parentheses, Roman numeral 2, phosphate. And I did that, I worked that through so you can see how I calculate that. Also, what I could, if you remember, is I said, if I look at the subscript for the anion, which is a 2, that's going to be the oxidation state for the iron, and that's what we calculated, right? Because didn't we not look at from the polyatomic ion table and find out that phosphate was -3? Yeah, and that turns out to be the subscript for the cation, right? So at a glance, I could have gone very quickly, go directly to iron, parentheses, Roman numeral 3, phosphate. But if you didn't see that, then work it through completely so you can see how those numbers add up. Remember, you got to add them up. Oh, I went too fast. Add them up. So let me back it up here. add up the charges so they add up to 0. Okay, so I gotta have enough of each positive in each cation and anion to add up to 0. All right, the iodine tetroxide. All right, base name iodine, okay, and then oxide. So there I put that in there, go back and do my prefixes. Tetra means 4, and di obviously means 2, so that is the formula, okay? Silver sulfate. Well, silver always has a +1. It is a group, one of the sweet 16, right? All right. And the sulfate, not sulfite, the sulfate, ATE, should send you to the polyionic table. And you would see that that is a SO4 -2, okay? I need 2 silvers for every sulfate. So the formula becomes Ag2SO4. Okay. All right. Here, note the IDE. Okay, it's a good example. Here, the ATE sends you to the polyionic table. This is the ATE. The IDE should tell you automatically it's the single element, which is the SUL, which is SULF, which is the sulfur, which has a -2 because it's a group 6 element, okay, non-metal, and we'll pick up 2 electrons. Nickel, in this case, is a +3 because you're being told that it's a Roman numeral 3. So now I have a dissimilar charge here, so I need common number, which would be 6. I need 2 nickels and 3 sulfides, so that becomes Ni2S3. Okay, there it is. All right. All right. All right, so don't forget the worksheet. That will help you out quite a bit, give you more practice to naming the compounds, okay? And that, ladies and gentlemen, brings you to the end of chapter 8. Okay. So, any questions before we continue? All right, well, chapter 9 deals with acids and bases. And there are quite a number of acids and bases that you're familiar with. Right now, as you sit there, there's one acid that's in your stomach, specifically hydrochloric acid. Now, way back when we were talking about covalent compounds and ionic compounds, I made the comment that one distinction between the two was that ionic compounds were, metal, non-metal combination, obviously. But what they all had in common was when you put them in water, ionic compounds would dissociate. Think of it as like 2 magnets, okay? And I put them in water and then they separate in solution into the respective ion, a full charge positive, full charge negative, okay? Now, some of these ions dissociate completely. Good examples are calcium hydroxide, sodium hydroxide, excuse me, very soluble in water, okay? But there are other ionic compounds that are not as soluble. And we're going to talk about that here, but what they do is they kind of still remain intact, but there's always a little bit that goes in solution. So in both cases, they will dissociate, except the magnitude varies from the solubility, okay? Then I said that covalent compounds, they will not dissociate. They stay intact, okay? With one exception. And I said an acids. Hydrochloric acid is a good example of a covalent compound that will dissociate. Now, as the case with the ionic compounds that dissociate in various degrees of magnitude, the same is true for acid. They will dissociate either 100%, very strong acid, or dissociate much less, okay? But before that, we get into that, and I want you to keep that in the back of mind. We need to figure out what defines an acid and what defines a base. Now, there's two definitions for an acid or a base. And I want to give you some additional information with respect to hydrogen. Hydrogen is a very unique element. Here we are with hydrogen in the upper left side, right here. It's not a metal, okay? It's not a metal, but we put it on the left, up in the first column, group 1. Why? Because it has one valence electron like the rest of the metals in that column, okay? One valence electron. Its electronic configuration, remember, 1s1, okay? And so we have hydrogen with one, remember the Lewis dot structures? Here's hydrogen at by itself, monatomic, with one valence electron. And its electron configuration was 1s1. Remember that? The s orbital, first energy level, 1 electron. Remember that electrons can, that orbital s can handle 2 electrons. So hydrogen is very unique in that it can pick up another electron. And when it does that, it has an overall negative charge, and we call that a hydride. Now, we're not going to talk a lot about the hydride, but it's used in chemistry for a lot of good purposes. Okay, so it's a hydride. Notice the IDE, like the chlorine went to chloride, right? Negative charge. That's a negative charge. Hydrogen goes to hydro. Okay. All right. So it has that unique property of hydrogen picking up an electron to form a hydride. And occasionally you might even find it in the periodic table in group 7 because of that capability. In some periodic tables, they got it right over the halogens, even though it's not a halogen, it has that capability of gaining 1 electron. All right, so, but just like the metals below it, it also has the capability of losing that 1 electron. And when it loses an electron, just like a metal, it ends up with a positive charge. That orbit, okay, is empty now. That's a 1s0. That orbit, the 1s orbit is empty. This is called a proton. This is what we attribute to the acidity of a solution. So meaning that any chemical that releases a proton, which is nothing more than a hydrogen with a plus charge, that is classified as an acid, okay? And hydrochloric acid, HCl, which is in your stomach, when that goes in solution, it will break apart, dissociate into a proton, and that is the acid. And that's why acidic, that's why you drink, like Malox or Tums, because that's the base which you ingest to reduce the acid content. This is a very important first type of reaction. So let me clear this up for a second. So once you generate a proton, anything that produces a hydroxide, remember the hydroxide? So this is a proton, which is nothing more than a hydrogen minus its electron. And this is a polyatomic ion. So on your polyatomic ion table, it's called the hydroxide, okay? And if we were doing the Lewis structure for the hydroxide, we would end up with a bond with the oxygen and then 3 pairs of lone electrons on the oxygen. The hydrogen has that orbit that is missing now because I lost that. So it's got an empty orbit over here. I'm going to put it, kind of, here's that orbit. So the hydroxide can take those 2 electrons and insert them into that empty orbit of the hydrogen. And guess what we create? good old-fashioned dihydrogen monoxide water. So whenever you get an acid and you react it with the base, you neutralize both the acid and the base, and you neutralize it to give you neutral water. That's your first reaction that we're going to be talking about in the next couple of chapters. This is called a neutralization reaction. Okay. So next time you are drinking, too much Taco Bell, you get a little too much hot chili or something, and you're dunking down some Tums, which is a base, regenerates hydroxide, or some Malox, okay, and you're drinking that, okay, you are neutralizing the excess acid you created in your stomach, and you're reducing it, so maybe give you some relief. Now, keep in mind, this reaction, for those of you that like alkaline water is nothing more than water that has high pH or greater. We're going to talk about the pH. 7 is neutral. Alkaline water is above 7. Well, when you ingest that, guess what? Your stomach is very strongly acid. It reacts with that. Any alkalines, any hydroxides that are in that water, you have neutralized with the protons that are in your stomach. Okay. And so any alkalinity that you have ingested has been neutralized to generate water. So and you create other salts. So there's all the alkalinity that you pay for is lost on ingestion. Okay, just some chemistry information for you there. All right, so there is a proton. These are proton ions, okay, hydrogen with the plus ions that are in water, okay? Some of the properties of acids obviously are, vinegar has acetic acid, and that is an organic acid. Citric acid, that's another organic acid. They all produce protons of very, very sour tasting, lemon and so forth, very sour tasting, and can be very corrosive, okay? There is a test you can do using what we call litmus paper. It's basically a go, no-go situation. There's blue litmus paper and there's red. If you take blue litmus paper and you put it in a solution and it changes that solution to red, that indicates you have an acid. That's all it tells you. It doesn't tell you anything else. So if blue litmus paper still remains blue, then you have a base. If the blue litmus paper changes color to red, then it's acidic, okay? Now, with respect to bases, those are any chemicals, like I stated, that produce the polyatomic ion hydroxide in water. We're talking about aqueous solutions here, okay? When it comes to acids and bases. There's such things like sodium hydroxide, potassium hydroxide, any metal you can put with hydroxide to form a base, because all of them will form a hydroxide solutions in water, and some of them will be strong and completely dissociate, and some not as much, but still produce a hydroxide. I wouldn't taste them, but they're very bitter. A good example of hydroxide, if you ever use liquid plumber at home to unclog your drain, and if you get some in your hand, you might find it to be kind of slimy. I don't recommend wear gloves, but if you do and it feels slimy, you might think it's the chemical, but it really is the hydroxide has denatured the skin and formed it into like a mush, and that's what you're feeling, okay? A lot of the FYI, for those of you who are using face preparations, if you read the label, you see that some of them have hydroxide, weak hydroxide solutions, alkaline. The point of that is to denature the skin and I guess clean it up, and just be careful because it can clean it up real well. And some people are sensitive to it. Okay, and that's why it feels soapy and slippery. It's because your skin is being broken down. Now, with respect to litmus paper test, there's, like I said, there's blue and red. So if you take red litmus paper and it changes it to blue, then you have a basic solution, okay? All right, so here's the first definition, okay? We had, like I said, there's two definitions of an acid and a base. They both have the common, sort of common definition for an acid. They're saying the same thing, just presenting it in a different kind of way. I'll demonstrate that here for a second. Arrhenius, scientist and old guy, long time ago, he defined as an acid as anything that produces a proton. So the example I gave was taking HCl, okay, and putting it into a solution. And this is the example of a covalent compound, but because the nature of the beast being an acid, it will break apart and dissociate, okay? This is what I mean by dissociation. It breaks into their respective ions. And so if you had a solution of pure water and you try to run current through it, light current, it won't conduct electricity because there's no ions. But the moment I put a little bit of HCl in there, it will start conducting electricity. It makes that water conductive, okay, because of the ions. Any water that has ions will conduct electricity. If there are no ions, there would be a non-conductor electricity. All right, so hydrochloric acid is a good example of an acid. A good example of a base. Now, most of the bases that you're going to be working with here are ionic compounds. The acids that you're working with are covalent compounds. Note the difference, right? So a base is a ionic compound, because if you look at this one here, it's sodium hydroxide, okay? Sodium hydroxide. Hydroxide is the polyatomic ion. Sorry, excuse my writing there. My pen went a little nuts there. That's sodium hydroxide. And being ionic, as I stated, one of the properties about ionic compounds, CPD compounds versus covalent acid, covalent compound. Okay, one of the properties of ionic compounds is they dissociate with various degrees of dissociation. This one, sodium hydroxide, literally dissociates at 100%. It's a very strong base. Why? Because it dissociates literally at 100%. Now, how do we know if it's going to dissociate 100% or much less? Well, good question. Okay, let me direct you to someplace that you may want to start reading, because we're going to use it quite a bit on the periodic table again. I do make reference to it a lot. On the bottom right corner, there is a table called solubility rules. And we're going to use that table to determine which ionic compound is soluble in water and which is insoluble. Okay, soluble in water infers literally 100%. Okay, 100% soluble. Insoluble means that now the bulk of it stays together, but maybe 5% of it goes in solution, but the bulk of it still, if it was a water solution, it would be intact and it would drop to the bottom of the container. Classic example of that would be milk and magnesia. If you ever looked at it and you let that bottle set, it will separate because the active ingredient isn't very soluble in water. You have to mix it up and form an emulsion, okay? And one thing about this solubility table is there's two columns. The column on the left is soluble. I call these guys the big four. When the cation is bonded to any of these metals, lithium, sodium, potassium, or ammonium, that ionic compound is always soluble, 100%. Previous example, I said sodium hydroxide. So anything that's bonded to sodium is soluble in water, okay? The other column, trust me, we're going to get in more detail here, just 2 columns. The other column is the insoluble. It just says it's insoluble, and as far as the physical state, we will put a letter S as a subscript. But keep in mind, even though the ionic compound is classified as insoluble, there's always a little bit that goes into solution, okay? Into solution. All right, so here we go, sodium hydroxide. Sodium is the cation, always 100% soluble. So these 2 are examples of what we would say or classifying as with respect to strength as strong. And the reason they're strong acids or strong base is simply because when they dissociate in water, literally they dissociate to 100%. So you've got tons of ions in solution, making it very strong. Okay. Now, this is the first reaction I talked about earlier, but specifically what it does whenever you react an acid with a base, you're always going to generate 100% water, okay? So if you're given a reaction if you're given this reaction, hydrochloric acid plus sodium hydroxide reacts and they get a question mark at the end. Well, you recognize if you're dealing with an acid, you recognize you're dealing with a base. That tells you automatically I'm making water because you're neutralizing the acid and the base. And then what's left over are the respective anions and cations of the acid and the base. So in this case, the sodium combines with the chloride to form the sodium chloride right here, okay? And then the proton reacts with the hydroxide to form water, okay? And what is formed is water plus the salt. Now, you might think salt is sodium chloride, and unfortunately, they use the example of sodium chloride, but keep in mind, salt in terms of chemistry is any ionic, well, right there, ionic compound. Any ionic compound is classified as a salt, okay? Not just table salt. So remember this. And now the other aspect to remember about an acid-base reaction is this. One proton requires 1 hydroxide to give you 1 molecule of water, okay? So that means that if I had 100 protons, I need 100 hydroxides to give me 100 waters. If I have 10 billion protons, then I need 10 billion hydroxides to give me 10 billion water molecules. It's a 1-to-1 relationship. And that, ladies and gentlemen, is an introduction to a chapter down the road where we talk about stoichiometry. How many of each reactants do we need to react to give us a product? In this case, that stoichiometry, that relationship is a 1-to-1, okay? A 1-to-1. And so I can use to predict if I have 100 molecules of protons, I can calculate how many molecules of water I'm going to make. And then eventually I can calculate how many grams of water that corresponds to. And that's all related to these calculations I've been mentioning way back when. We're using that method, I mentioned of basically keeping track of the units so we can back calculate and start doing calculations down the road. And there's a good example here. If I start off with 10 grams of protons, how many grams of water am I going to make? Okay, and before I can answer that question, I got to write the reactants and then balance them up to make sure I got the correct number of each, so I can calculate how much product I'm going to make, okay? So this is the beginnings of the types of reactions we're going to eventually work with. All right, the other definition, we got the Arrhenius definition of acid or base, anything that produces a proton. Did I go over time? I think I did, guys. All right, yeah. Give me 2 minutes. I guess this started a little bit late. Arrhenius acid, anything that produces a proton or a base. Now we have a different definition, which encompasses more chemicals to be able to define, because before, to become a base, you can be a base and have nothing to do at all with hydroxide, okay? And here's the deal. The Bronsted-Lowry base is basically, they define an acid as anything that is a proton donor. Well, you think about it, it's like the Arrhenius definition, anything that produces a proton. So in essence, they're still producing, whether they lose it or produce it, they're making a proton in both cases. But Arrhenius definition is anything that is a proton donor, okay? And the base, this is where they differ. The base is any chemical that will accept that proton and entangle itself with it, bond with it. If you recall, when we did the Lewis dot structure for ammonia, remember that? Ammonia had a lone pair of electrons on there, a lone pair. I just stated that the proton has an empty orbital, okay? And like I demonstrated earlier with the hydrogen and the chloride, well, the same thing can occur here. What's happening, that lone pair can insert itself into that empty orbital of the hydrogen, forming a complex. Specifically, we did the Lewis dot structure for the ammonium ion. Remember that one? Where we had 4 protons around it, and we did the bracket and the charge, okay? And so the ammonia here acts as a Bronsted-Lowry base because it's accepting that proton and neutralizing it by taking the lone pair of electrons and creating a bond with that proton, okay, to form the ammonium, form a salt. In this case, it's called ammonium chloride. This is the polyatomic ion, the only one that was positive, which is ammonium chloride, name-wise. You could have ammonium fluoride, ammonium whatever anion you have, okay? So there's where they differ with respect to definitions, is that the base accepts that proton. All right, well, let me stop it here. Yeah, slide 6. And then we'll go through some more examples. The next steps will be slides are fairly quick. All right, let me stop it here.